Hello everyone, good morning to all. In the યુએનઆઈસીપી સબ્જેક્ટની અંદર આપણે ડિસ્કસ કરી રહ્યા હતા જુદા જુદા પ્રકારના કંટ્રોલ મોડ્સ અને એક્શન્સ એટલે કે કોઈ પણ સિસ્ટમ હોય છે બરાબર તો એને કંટ્રોલિંગ કઈ રીતે કરી શકાય છે યુઝિંગ ધ કંટ્રોલર્સ ઓકે so in fully automized system there is using the controllers so these are the p control I control that means proportional control integral control PI control okay then PID control so basically we discuss only two types that is P and I then that is proportional control then after integral control so at last we discuss the differentiations of the proportional integral control so which are the control law and transfer function we discuss so in which we discuss also the response characteristic which limit should be applied for the complete transfer function so now the remaining theorem will be continued here the within integral time tau 1 integral actions repeat the proportional actions once that means proportional actions is doing at once then this repetitions occurs at every tau minutes and every tau minutes that for the fixed time it will be repeated every tau 1 and here it is called as a tau 1 is a reset time one revolution or a one control signal is applied then after tau 1 time it will be a reset time and then it is again send it to the signal to the PI controller so the integral time tau 1 is defined as the time needed by the PI controller to repeat the initial P actions hence tau 1 is expressed in the unit of minutes or minutes per repeat that will be considered as a minutes per repeat okay so some PI controllers are calibrated in terms of reset time that is TR equal to 1 by tau 1 expressed as repeat per minute so what is reset wind up so let's look at it as I explained earlier the output of PI controller change continuously until it attains the value required to make steady state offset to 0 that means SP and VP SP and VP both are equal so the it occurs the steady state offset so the desirable actions occurs until the controller output changes to the extreme value is defined by the range of percentage 0 to 100% okay in between them so the final control elements such as a control valve gets completely open or closed so this condition is known as a saturation or integral wind up if error still persists even after the controller gets saturated it is unable to bring the control variable PV back to the set point and the condition occurs when the disturbance or a set point change so large then it is beyond the range of MV during the startup shutdown or change over the operations so this phenomena is also given um, in the graph which is the value of YSP versus y of t versus t and the effect of constant t and constant kc the disadvantages of using I controller action is that is produce oscillations behavior for એટ દેટ પોઈન્ટ જેટલું પણ ઉપર ડાયરેક્શનની અંદર થશે એટલું જ ઓસ્કિલેશન્સ નીચેની લાઇનમાં પણ થશે. And this one is controlled by which may be reduced stability of the stability of the system. So here they are the effect of Kc and effect of tuning parameter T1, tau1 and Kc. So here we can see that Kc1 is greater than Kc2. Okay, so Kc1 is greater oscillations, where here the second figure at the right hand side which indicates the tau1. So tau1 is less than the tau2. Okay, so increasing in the value of tau1. So this one is the effect of tuning parameters of PI controller. So now let's see effect of Kc on 8.10a. This figure shows the effect of Kc on output response at constant tau1. As Kc is increased, the output response becomes faster but more oscillatory with increasing overshoot and the decay ratio. Okay, then effect of tau1 8.10b shows the effect of tau1 on the output response at as Ti is decreased, reset or integral actions increasing, with the result in increased faster but more oscillatory response with increased overshoot and decay ratio. Okay, so these are the effect of Kc and tau1. So now the next controller is that proportional integral derivative control action, PID controller. This is also important. PID. First, the controller low. The output of a PID controller is given by these equations. OP of T is equal to OP of SS plus KCE plus Kc tau1 integrating from 0 to T E of dt plus Kc tau d dE by dt. So from the ઇક્વેશન ની અંદર આપણે શું કર્યું છે, ત્રણ ઇક્વેશનનું એડિશન કર્યું છે, પી આઈ અને ડીનું. બરાબર. હવે કમાન્ડ સિગ્નલ કયો મળે છે? કમાન્ડ સિગ્નલ સી ઓફ ટી ઇઝ ઇક્વલ ટુ ઓપી ઓફ ટી માઇનસ ઓપી ઓફ એસએસ. સો રિમેનિંગ વિલ બી like that, Kc of E plus Kc by tau1 is common. Kc by, so dt is common. Kc by tau1. So integrations 0 to t E of dt plus Kc tau d dE by dt, and the transfer function from the equation 8.21, it becomes the Laplace transformer. Take a Laplace transform for the equations 8.21. So જેના માટે Laplace transform શું થશે? C of S is equal to Kc 1 plus 1 upon tau1s plus TDS. પહેલાનું શું થશે? K C છે એ બંનેમાંથી કોમન લઈ લીધું. બરાબર, બધી જ જગ્યાથી. તો એનું શું થશે? 1 થશે, સિંગલ છે એટલે. પછી 1 upon tau1, તો 1 upon single 1 upon tau1s, then TDS. બરાબર, TDS into E of S, બંનેમાંથી E of S પણ કોમન. એન્ડ દેન ટ્રાન્સફર ફંક્શન શું થશે? C by S upon E by S, so that is Kc 1 plus 1 upon tau1s plus TDS. Response characteristic. We have seen that in the case of PI controller, due to the effect of increasing Kc and decreasing tau1, the output response becomes faster but more oscillatory. The output response becomes faster, but it is more as oscillatory, which may lead to instability of D mode is added to the PI controller, and it brings a stabilizing effect of the system. So PID controller gives reasonably fast speed of response with moderate overshoots and decay ratio. Okay, so એના માટે જોઈએ આપણે ફિગર 8.2. So PI and P control only, PID control, PI and PID. Okay, so and I control. So 8.12 shows the comparison of output response of characteristic P, PI અને PID. P, PI અને PID. So here is the graph is given that y of t versus t, in which the curvature line is indicate that no control. Below the no control line it is a P control line only P control line, and then it is after the below it is the PI controller. The oscillating layer is positive, negative and increasing with respect to time, and the PID compared to the PI control it can be more clear. Okay, now on off controller, simple on off, switch is on, then the controller is on, and the off, that means simply it's off. So on off controller એટલે કે ટુ પોઝિશન્સ ઓફ બેંગ કંટ્રોલર, અને બીજું કહેવામાં આવે છે આ પોઝિશન્સને ટુ પોઝિશન્સ ઓર બેંગ કંટ્રોલર. ટુ કંટ્રોલર અથવા ટુ પોઝિશન્સ અથવા બેંગ કંટ્રોલર. The controller law. The output of an ideal on-off controller has only two possible extreme values without any intermediate values, depending on whether error is positive. The output of an controller, the output of an ideal on-off controller has two permissible extreme values without an intermediate, and which is depends upon whether error is positive or a negative. Error શું છે, પોઝિટિવ છે કે નેગેટિવ? એના ઉપર ઓન ઓફ કંટ્રોલર વર્ક કરે છે. સો ઇટ ઇઝ SP is greater than PV or SP is less than PV. So optimum time for the operational, that is OP of T, which is equal to OP of maximum if the error is equal to greater than or equal to 0 condition, that is an on condition. When error is greater than or equal to 0, it is called on condition, and OP minimum if the error is less than 0, then it is the condition is off controller. Now for a typical digital electronic controller, that should be a variation is that for the digital electrometer 100%, that means 20 milliampere, and 0% that means maximum and minimum that is 0, that is 4 milliampere. And for pneumatic controller, air to open or air to close controller, so exactly for this, if the OP maximum, operating maximum, which is maximum is 100%, so એના અંદર પ્રેશર જે છે, મેક્સિમમ પ્રેશર કેટલું કન્સિડર કરવાનું છે, 15 psi, or the OP is minimum value is 0%, and minimum value it consists up to 3 psi. Okay, so there is a number of two controller actions. First electronic controller, second one is pneumatic controller. So in the both of them, so the difference is that 100 percentage of PSI and 0 percentage of PSI.